So far, our discussion about networks has focused on analyzing network structures, so really thinking about static networks and being able to measure them, and then also talking a little bit about changes in network structure, whether that's part of the growth processes or part of the kind of natural failures or possibly attacks on systems. So now in this class, we're moving towards processes on networks, and this really involves now a whole other layer that exists on top of the network. So just as everything that we've done before, the premise behind all of this is that in some way or another, the topology of the network is important for understanding how this other process evolves. And so the intuitive thing is to say that essentially if nodes have edges between them, that they somehow interact in terms of this process. And so this process could be modeling all sorts of different things. It could be talking about infection models, something we'll talk about very specifically. It could be talking about simply opinion dynamics. About how a person in the population may be feeling about a particular candidate for an election or product that's being released by a new, like a new consumer good. So there's all sorts of things that could be modeled, and typically the idea here is that we're going to quantify whatever is important about the system, and we're going to call that the state. And so that could be essentially a number from 0 to 1 that describes how much, what the probability is that someone's going to buy a new phone, for example, or it could be the probability that someone is actually infected by a disease, or it could be the amount of wealth that they have, for example. And again, that so the idea here is that we have a state, and what we're doing is using either some sort of rule. So typically we think about that as being a differential equation or a difference equation. And that rule describes how this process changes, essentially the behavior of this process over time. And so if it's an infection spread, essentially what does the infection look like across the population that would be the network, and how does that change as time moves along? And so the idea is that these differential equations provide a rule that tells us how to update the state. So how at one point in time we can then update the state to in the next point in time. Most of the time these states are assigned to node values. So that means that a node is carrying essentially the important information about the behavior of the network, but that's not always true. That's going to be true for everything we see in this class, but it's certainly possible that you could represent states that exist on edges. And so that could be, for example, a process that changes the capacity as a function of time. So in some of our first examples, we're going to see essentially very simple dynamic models where nodes simply pass their state to their neighbors. And so this isn't very sophisticated. It also doesn't have any sort of memory. So instead, the node value at one time becomes that value passes its node, that state value, onto all of its neighbors. And that could be whether it's undirected or it could be directed. In more sophisticated models, then finally we'll have something where it really makes sense to have the state representing something about that system, and that gets updated, informed by its neighborhood, but not solely determined by it. So depending on what we're trying to model, we have different sophistication levels. But again, the overarching idea is the fact that somehow the structure of the network tells us information about how this process is evolving because of how the states are affecting each other. Before we go too deep into talking about processes and differential equations on networks, it's worth stepping back and taking a look at something that you definitely have seen before, which is just the solution to a single differential equation. And so this is the case where the state is x and it's a scalar value, and you have a parameter a, and this is the type of equation that could model, for example, an interest-bearing savings account, or it could represent the population growth. And so this a would represent the rate parameter or the interest rate, depending on the application. So another way to represent so what this differential equation is actually telling us is this x dot represents the time change of that state. And so that's exactly what this derivative is, that's dx dt. And so just rewriting what the differential equation is, it's ax. And so in this case, this is a separable differential equation, and which means that I can move all of the x information on one side and all the a and time information onto the other. And so that leads me with everything that's related to x on this side and everything that's related to t, or everything else, on the other side. And then I can integrate those sides. And so this integral of 1 over x dx is going to turn into the log function, the natural log function. And then the integrand on the right-hand side doesn't actually have the variable t in it, so you just get a linear copy of t, so you get at and then plus some constant, which I'm calling c tilde. So when you exponentiate both sides, you take the exponential of both sides, the e to this piece and the e to this whole side, the natural log and the exponential cancel, and so you're left with the state back again. And that shows how this differential equation gives rise to dynamics that are essentially an exponential equation. And so this is something you've seen probably many times. Using exponential rules, we can bring this c tilde out in front, and this c is really e to the c tilde. But effectively, this c captures initial conditions, and e to the at describes the behavior over time. And so remember, when you're dealing with a differential equation, this differential equation has x's and x dots in it. When we get to the solution, we have x as a function of time, which means that the right-hand side here essentially is just a function of time. So it's no longer a function of x. So this is really what the behavior looks like if you plotted it out over time. And so now when we look just kind of generically at network dynamics or processes that could be evolving on a network, then what we're interested in doing is writing down a differential equation that represents the time change of the state at a particular node. So if we're looking specifically at node I, and we're looking at the state of node I, then x dot of sub I tells us how x of I is changing as a function of time. And so what we break this into is some part that is related to just the node itself. So this could be essentially what we call intrinsic dynamics. And so, for example, a lot of the work that I'd be interested in doing with networks relates to neuroscience. And so neurons have their own intrinsic dynamics and even nonlinear dynamics that kind of tell how that neuron would behave if it was just by itself and not connected to anything else. Then there's another piece, and that's what this other piece here quantifies, is how the dynamics change depending on what it's connected to. And so in this case, we're taking a sum over all of the possible nodes. So j goes from 1 up to n. And it's the responsibility of the adjacency matrix here, aij, to essentially be non-zero if there is a connection, and 0 if there is not a connection. So essentially this is, you can think about this as kind of being a masking variable that only allows there to be an interaction between I and j, and therefore a contribution to its differential equation if aij is non-zero. So if aij is 0, there is no contribution because they're not connected in any way. But if they are neighbors, and if this is directed, then you'd have to include direction in here. But right now we're considering an undirected graph. So here, this aij allows this function to tell how xi and xj and the relationship between them influence the rate of change of xi. So we'll see a couple specific examples. This is really just saying that there is a function that includes variables xi and xj that tell us how it changes xi. Oftentimes in the context of networks, simply because usually we don't have another alternative. For example, we don't have data that would describe each individual neuron. We assume that they all have the same kinds of behaviors. And so that means that we lose this f sub I and this gij. So now we just have a single function g and a single function f. So f represents the intrinsic dynamics and g represents the connectivity dynamics. And again, we're going to see a couple different examples of how you can form each one of these depending on what kinds of processes that you want to have. So this f and this g function become specialized depending on what you want to do. But this piece that has this sum over the nodes masking by the adjacency matrix, this is something that's common, and you'll see throughout all of the connectivity models that we want to talk about related to processes on networks.